5, 4. Okay, this is the lecture on positive definite matrices. I made a start on those briefly in a previous lecture, and one point I wanted to make was the way that this topic brings the whole course together. Pivots, determinants, eigenvalues, and something new and stability, and then something new in this expression x transpose AX. Actually, that's the guy to watch in this lecture. So the topic is positive definite matrix, and what's my goal? First goal is, how can I tell if a matrix is positive definite? So I would like to have tests to see if you give me a 5 by 5 matrix, how do I tell if it's positive definite? More important is, what does it mean? Why are we so interested in this property of positive definiteness? And then at the end comes some geometry. Ellipses are connected with positive definite things. Hyperbolas are not connected with positive definite things. So there's a geometry too, but mostly it's linear algebra. And this application of how do you recognize when you have a minimum is pretty neat. Okay, I'm going to begin with 2 by 2. All matrices are symmetric, right? That's understood. The matrix is symmetric. Now my question is it positive definite? Now here are some, each one of these is a complete test for positive definiteness. If I know the eigenvalues, my test is, are they positive? Are they all positive? If I know so A is really, I look at that number A here as the 1 by 1 determinant, and here's the 2 by 2 determinant. So this is the determinant test. This is the eigenvalue test. This is the determinant test. Are the determinants growing of all n, sort of, could I call them leading submatrices? They're the first ones. They're the northwest Seattle submatrices coming down from there. All those determinants have to be positive. And then another test is the pivots. The pivots of a 2 by 2 matrix are that number A, for sure. And since the product is the determinant, the second pivot must be the determinant divided by A. And then in here is going to come my favorite and my new idea, the one to catch about x transpose AX being positive. But we'll have to look at this guy. This gets like a star because for most presentations, the definition of positive definiteness would be this number 4, and these numbers 1, 2, 3 would be tests for it. Okay, maybe I'll tuck this wire in a little bit. Okay, so I'll have to look at this x transpose AX. Can we just be sure? How do we know that the eigenvalue test and the determinant test pick out the same matrices? And let's just do a few examples. So examples. Let me pick the matrix 2, 6, 6. Tell me, what number do I have to put there for the matrix to be positive definite? Tell me a sufficiently large number that would make it positive definite. Let's just practice with these conditions in the 2 by 2 case. Now, when I ask you that, you don't want to find the eigenvalues. You would use the determinant test for that. So the first, or the pivot test, that guy is certainly positive. That had to happen. and it's okay. How large a number here? The number had better be more than what? More than 18, right? Because if it's no. More than what? 19, is it? If I have a 19 here, is that positive definite? Yeah, because I get 38 minus 36. That's okay. If I had an 18, let me play it really close. If I have an 18 there, then am I positive definite? Not quite. I would call this guy positive. So it's useful just to see that this is the borderline. That matrix is on the borderline. I would call that matrix positive semi-definite. And what are the eigenvalues of that matrix? Just since we're good at eigenvalues of 2 by 2s. When it's semi-definite, but not definite, then I'm squeezing this eigenvalue test down. Tell what's the eigenvalue that I know this matrix has? What kind of a matrix have I got here? It's a singular matrix. One of its eigenvalues is 0. That has an eigenvalue 0, and the other eigenvalue is, from the trace, 20. Okay, so that matrix has eigenvalues greater than or equal to 0. And it's that equal to that brought this word semi-definite in. And what are the pivots of that matrix? So the pivots, so the eigenvalues are 0 and 20. The pivots are, well, the pivot is 2. And what's the next pivot? There isn't one. We got a singular matrix here. It'll only have one pivot. You see that that's a rank 1 matrix. 2, 6 is 6, 18 is a multiple of 2, 6. The matrix is singular. It only has one pivot. So the pivot test doesn't quite pass. Let me do the X transpose AX. Now this is the novelty now. Okay. What am I looking at when I look at this new combination X transpose AX? X is any vector now. So let me compute. So any vector, let me call its components x1 and x2. So that's X. And I put in here A. Let's use this example, 2, 6, 6, 18. And here's X transpose, so x1, x2. We're back to real matrices. After that last lecture that said what to do in the complex case, let's come back to real matrices. So here's X transpose AX, and what I'm interested in is, what do I get if I multiply those together? I get some function of x1 and x2. And what is it? Let's see. If I do this multiplication, should I do it? I'll just do it slowly. x1, x2, if I multiply that matrix, this is 2x1 and 6x2s. And the next row is 6x1s and 18x2s. And now I do this final step. And what do I have? I've got 2x1 squareds. That 2x1 squareds is coming from this 2. I've got, this one gives me 18. Well, shall I do the ones in the middle? How many x1, x2s do I have? Let's see, x1 times that 6x2 will be 6 of them. And then x2 times this one will be 6 more. I get 12. So in here is going, this is the number A. This is the number 2b. And in here is going to, x2 times 18x2 will be 18x2 squareds, and this is the number c. So it's ax1, it's like ax squared, 2bxy and cy squared. So my first point that I wanted to make by just doing out a multiplication is that as soon as you give me the matrix, those are the numbers that appear in the, I'll call this thing a quadratic. You see, it's not linear anymore. AX is linear, but now I've got an X transpose coming in. I'm up to degree 2. Up to degree 2, maybe quadratic is the usual word, a quadratic form. It's purely degree 2. There's no linear part, there's no constant part, there certainly aren't any cubes or fourth powers. It's all second degree. And my question is that quantity positive or not? That's for every x1 and x2. That is my new definition. That's my definition of a positive definite matrix. If this quantity is positive, if it's positive for all x's and y's, all x1, x2's, then then that's the matrix is positive definite. Now, is this guy passing our test? Well, we anticipated the answer here by asking first about eigenvalues and pivots, and what happened? It failed. It barely failed. If I had made this 18 down to a 7, it would have totally failed. Can I do that with the eraser, and then I'll put back 18, because 7 is such a total disaster that I'll keep 7 for a second. Is that thing in any way positive definite? No, absolutely not. I don't know its eigenvalues, but I know for sure one of them is negative. Its pivots are 2, and then the next pivot would be the determinant over 2, and the determinant is, what's the determinant of this thing? 14 minus 36, so I've got a determinant of minus 22. The next pivot will be, the pivots now of this thing are 2 and minus 11 or something. Their product being minus 22, the determinant. This thing is not positive definite. Let me look at the X transpose AX for this guy. If I do out this multiplication, this 18 is temporarily changing to a 7. This 18 is temporarily changing to a 7. And I know that there's some numbers, x1 and x2, for which that function is negative. And I'm desperately trying to think what they are. Maybe you can see. Can you tell me a value of x1 and x2 that makes this quantity negative? Oh, maybe 1 and minus 1? Yeah, in this case, that will work, right. If I took x1 to be 1 and x2 to be minus 1, then I always get something positive, the 2 and the 7, minus 1 squareds. But this would be minus 12, and the whole thing would be negative. I'd have 2 minus 12 plus 7, I'm negative. If I drew the graph, can I get a little picture in here? If I draw the graph of this thing, so graphs of the function f of xy, or f of x, shall I say, or f of xy equal this, it's this x transpose ax, this ax squared, 2bxy, and cy squared. And let's take the example with these numbers. Okay, so here's the x-axis, here's the y-axis, and here's up is the function. Z, if you like, or f. I apologize, and let me just once in my life here put an arrow over these x's so you see that that's the vector, and I just gave, instead of x1 and x2, I made them the components x and y. Okay, so what's a graph of 2x squared, 12xy, and 7y squared? I'd like to see, to get some idea, actually I'm not the greatest artist, but tell me something about this graph of this function. Well, tell me one point it goes through. The origin, right? Even this artist can get this thing to go through the origin. When these are 0, I certainly get 0. Okay, some more points. If x is 1 and y is 0, then I'm going upwards. So I'm going up this way. I'm going up like 2x squared in that direction. So that's meant to be a parabola. And suppose x stays 0 and y increases. Well, y could be positive or negative. It's 7y squared. Is this function going upward? In the x direction, it's going upward. And in the y direction, it's going upwards. And if x equals y, in the 45-degree direction, it's certainly going upwards. Because then we'd have, what about, everything would be positive. But what? This function, what's the graph of this function look like? Tell me the word that describes the graph of this function. This is the non-positive definite. Everybody's with me here. I'm, for some reason, got started in a negative direction here, a case that isn't positive definite. And what's the graph look like? It goes up, but do we have a minimum here? Does it go up from the origin completely? No, because we just checked that this thing failed. It failed along the direction when x was minus y. We have a saddle point. Let me at least tell you the word. This thing goes up in some directions, but down in other directions. And if we actually knew what a saddle looked like, I think saddles do that. Like, am I right? I mean, like the way your legs go is like down, and the way you, and looking like forward and, and drawing the thing is even worse than describing it. I'm just going to say, in some directions we go up, and in other directions, there is a saddle. Now, I'm sorry I put that on the front board because I have no way to cover it. But it's a saddle. Okay. And this is a saddle point. It's a point that's at the maximum in some directions and at the minimum in other directions. And actually, the perfect directions to look are the eigenvector directions. We'll see that. So this is not a positive definite matrix. Okay, now I'm coming back to this example. Getting rid of this 7, let's move it up to 20. Let's make the thing really positive definite. Okay. So this number is now 20. C is now 20. Okay. Now that passes the test, which I haven't proved, of course. It passes the test for positive pivots. It passes the test for positive eigenvalues. How can you tell that the eigenvalues of that matrix are positive without actually finding them? Of course, 2 by 2, I could find them. But can you see, how do I know they're positive? I know that their product is, I know that lambda 1 times lambda 2 is positive. Why? because that's the determinant, right? Lambda 1 times lambda 2 is the determinant, which is 40 minus 36 is 4. So the determinant is 4. And the trace, the sum down the diagonal, is 22. So they multiply to give 4. So that leaves the possibility they're either both positive or both negative. But if they're both negative, the trace couldn't be 22. So they're both positive. So both of the eigenvalues there are positive. Both of the pivots are positive. The determinants are positive. And I believe that this function is positive everywhere except at 0, 0, of course. When I write down this condition, so I believe that X transpose, let me copy, X transpose AX is positive except, of course, at the minimum point at the 0 vector. Of course, I don't expect miracles. So what does its graph look like? And how do I check that this really is positive? So we take its graph for a minute. What would be the graph of that function? It does not have a saddle point. I'll raise the board here and stay with this example for a while. So I want to do the graph of, here's my function, 2x squared, 12xy's, that could be positive or negative, and 20y squared. My point is, you're seeing the underlying point is that the things are positive definite when in some way these pure squares we know to be positive. And when those kind of overwhelm this guy, who could be positive or negative, because x and y could have same or different signs, when these are big enough, they overwhelm this guy and make the total thing positive. And what would the graph now look like? Let me draw the x. Well, let me draw the x direction, the y direction, and the origin. At 0, 0, I'm there. Where do I go as I move away from the origin? Where do I go as I move away from the origin? I'm sure that I go up. The origin, the center point here, is a minimum, because this thing, I believe, and we better see why, the graph is like a bowl. The graph is like a bowl shaped. Here's the minimum. And because we've got a pure quadratic, we know it sits at the origin. We know its tangent plane, the first derivatives, are 0. So we know first derivatives are all 0. But that's not enough for a minimum. First derivatives were 0 here. So the partial derivatives, the first derivatives, are 0 again, because first derivatives are going to have an x or a y in them. They'll be 0 at the origin. It's the second derivatives that control everything. It's the second derivatives that this matrix is telling us. And somehow so here's my point. You remember in calculus, how did you decide on a minimum? First requirement was that the derivative had to be 0. But then you didn't know if you had a minimum or a maximum. To know that you had a minimum, you had to look at the second derivative. The second derivative had to be positive. The slope had to be increasing as you went through the minimum point. The curvature had to go upwards. And that's what we're doing now in 2 dimensions and in n dimensions. So we're doing what we did in calculus. Second derivative positive will now become that the matrix of second derivatives is positive definite. Can I just, so this is like the translation of this is how minimum is coming in. In the beginning of calculus, we had a minimum was associated with second derivative being positive, and first derivative 0, of course. Derivative, first derivative, but it was the second derivative that told us we had a minimum. And now in 1806, in linear algebra, we'll have a minimum. For our function now, our function will be a function not of just x, but several variables, the way functions really are in real life. The minimum will be when the matrix of second derivatives, the matrix here was 1 by 1. There was just one second derivative. Now we've got lots. Is positive definite. So positive for a number translates into positive definite for a matrix. And it just brings everything together. You check pivots, you check determinants, you check eigenvalues, or you check this minimum stuff. Okay, let me come back to this graph. That graph goes upwards. And I have to see why. How do I know that this function is always positive? Can you look at that and tell that it's always positive? Maybe 2 by 2 you could feel pretty sure. But what's the good way to show that this thing is always positive? If we can express it as in terms of squares, because that's what we know for any x and y, whatever, if we're squaring something, we certainly are not negative. So I believe that this expression, this function, could be written as a sum of squares. Can you tell me? See, because all the problems, the headaches are coming from this xy term. If we can get expressions, if we can get that inside a square. So actually, what we're doing is something called, that you've seen called completing the square. Let me start the square and you complete it. Okay, I think we have 2 of x plus, now I don't know how many y's we need, but you'll figure it out, squared. How many y's should I put in here to make, what do I want to do? The 2x squareds will be correct, right? What I want to do is put in the right number of y's to get the 12xy correct. And what is that number of y's? Let's see, I've got 2 times, and so I really want 6xy's to come out of here. I think maybe if I put 3 there, does that look right to you? I have 2. This is, we can mentally multiply that out. That's x squared, that's right. That's 6xy times the 2 gives this one, right? And how many y squareds have I now got? How many y squareds have I got from this term? 18. 18 was the key number, remember? Now, if I want to make it 20, then I've got 2 left, 2 y squareds. That's completed the square. And it's, now I can see that function is positive because it's all squares. I've got 2 squares added together. I couldn't go negative. What if I went back to that 7? If instead of 20, that number was a 7, then what would happen? This would still be correct. I'd still have this square. to get the 2x squared and the 12xy, and I'd have 18y squared, and then what would I do here? I'd have to remove 11 y squareds, right? If I only had a 7 here, then instead of, when I had a 20, I had 2 more to put in. When I had an 18, which was the marginal case, I had no more to put in. When I had a 7, which was the case below 0, the indefinite case, I had minus 11. Okay, now, so you can see now that this thing is a bowl. It's going upwards. If I cut it at a plane z equal to 1, say, I would get a curve. What would be the equation for that curve? If I cut it at height 1, the equation would be this thing equal to 1. And that curve would be an ellipse. So actually, already I've brought into the lecture the different pieces that we're aiming for. We're aiming for the tests, which this passed. We're aiming for the connection to a minimum, which we see in the graph. And if we chop it if we set this thing equal to 1, if I set that thing equal to 1, what that gives me is the cross section. It gives me this curve, and its equation is this thing equals 1, and that's an ellipse. Whereas if I cut through a saddle point, I'll get a hyperbola. Okay, but this minimum stuff is really what I'm most interested in. Okay. But I just have to ask, do you recognize, I mean, these numbers here, the 2 that appeared outside, the 3 that appeared inside, the 2 that appeared there, actually, those numbers come from elimination. Completing the square is our good old method of Gaussian elimination expressed in terms of these squares. Let me show you what I mean. I just think those numbers are no accident. If I take my matrix 2, 6, 6, and 20, and I do elimination, then the pivot is 2, and I take 3. Oh, yeah, what's the multiplier? How much of row 1 do I take away from row 2? 3. So what you're seeing in this completing the square is the pivots outside and the multiplier inside. Should just do that again. The pivot is 2. 3 of those away from that gives me 2, 6, 0. And what's the second pivot? 3 of this away from this. 3 6s will be 18, and the second pivot will also be a 2. So that's the U. This is the A. And, of course, the L was 1, 0, 1, and the multiplier was 3. So completing the square is elimination. Why am I happy to see that coming together? Because I know about elimination for n by n matrices. I've just started talking about completing the square here for 2 by 2s. But now I see what's going on. Completing the square really amounts to splitting this thing into a sum of squares. So what's the critical thing? I have a lot of squares, and inside those squares are multipliers, but there's squares. And the question is, what's outside these squares? When I complete the square, what are the numbers that go outside? They're the pivots. They're the pivots. And that's why positive pivots give me sum of squares. Positive pivots Those pivots are the numbers that go outside the squares. So positive pivots, sum of squares, everything positive, graph goes up, a minimum at the origin. It's all connected together. All connected together. And in the 2 by 2 case, you can see those connections. But linear algebra now can go up to 3 by 3, n by n. And let's do that next. Can I just, before I leave 2 by 2, I've written this expression, matrix of second derivatives. What's the matrix of second derivatives? That's one second derivative now, but if I'm in 2 dimensions, I have a 2 by 2 matrix. It's the second x derivative. The second x derivative goes there. Shall I write it? Yeah, I better use this is fxx, if you like. fxx. That means the second derivative of f in the x direction. fyy, second derivative in the y direction. Those are the pure second derivatives. They have to be positive for a minimum. This number has to be positive for a minimum. That number has to be positive for a minimum. But that's not enough. Those numbers have to somehow be big enough to overcome this cross derivative. Why is the matrix symmetric? Because the second derivative of f with respect to x and y is equal to, that's the beautiful fact about second derivatives, is I could do those in either order and I get the same thing. So this is the same as that. And that's the matrix of second derivatives. And the test is it has to be positive definite. You might remember from tucked in somewhere near the end of 1802, or at least in the book, was the condition for a minimum for a function of 2 variables. When do you have a minimum for a function of 2 variables? And believe me, that's what calculus is for. The condition is first derivatives have to be 0. And the matrix of second derivatives has to be positive definite. So you maybe remember there was an fxx times an fyy that had to be bigger than an fxy squared. That's just our determinant 2 by 2. But now, we now know the answer for 3 by 3, n by n, because we can do elimination on n by n matrices. We can connect to eigenvalues of n by n matrices. We can do sum of squares, sum of n squares instead of only 2 squares. And so let's take let me go over here to do a 3 by 3 example. So 3 by 3 example. Okay. Oh, let me use, shall I use my favorite matrix? You've seen this matrix before, I guess. Well, let's use the good matrix. Why not? That's, okay. Is that matrix positive definite? So I'm going to ask questions about this matrix. Is it positive definite, first of all? What's the function associated with that matrix? What's the x transpose AX? Do we have a minimum for that function at 0? And then even what's the geometry? Okay. First of all, is the matrix positive definite? I've given you the numbers there, so you can take determinants. Maybe that's the quickest. Is that what you would do mentally? If I give you a matrix on a quiz and say, is it positive definite or not? I would take that determinant, and I'd get the answer 2. I would take that determinant and I would get the answer for that 2 by 2 determinant. I get the answer 3. And anybody remember the answer for the 3 by 3 determinant? It was 4. You remember for these special matrices, when we did determinants, they went up 2, 3, 4, 5, 6. They just went up linearly. So that matrix has the determinants are 2, 3, and 4. Pivots. What are the pivots for that matrix? I'll tell you. The first pivot is 2. The next pivot is 3 over 2. The next pivot is 4 over 3. Because the product of the pivots has to give me those determinants. The product of these two pivots gives me that determinant. The product of all the pivots gives me that determinant. What are the eigenvalues? Oh, I don't know. Yeah, the eigenvalues, I've got, what do I have, a cubic equation, a degree 3 equation. There are 3 eigenvalues to find. If I believe what I've said today, what do I know about these eigenvalues? Even though I don't know the exact numbers. I might, actually, I think I remember the numbers. Because these matrices are so important that people figure them out. But what do you believe to be true about these 3 eigenvalues? You believe that they are all positive, right? They're all positive. I think that they are 2 minus square root of 2, 2, and 2 plus the square root of 2. I think. Let me just... I can't write those numbers down without checking the simple checks. The first simple check is the trace. So if I add those numbers, I get 6, and if I add those numbers, I get 6. The other simple test is the determinant. Am I going to do this? Can you multiply those numbers together? I guess we can multiply by 2, okay. What's 2 minus square root of 2 times 2 plus square root of 2? That'll be 4 minus 2. That'll be 2. Yeah, 2 times 2. That's got the determinant right. So it's got a chance of being correct, and I think it is. Now, what's the X transpose AX? I better give myself enough room for that. X transpose AX for this guy. It's 2 x1 squareds. And 2 x2 squareds. And 2 x3 squareds. Those come from the diagonal. Those were easy. Now, off the diagonal, there's a minus and a minus. They come together. There'll be a minus 2. And minus 2 whats are coming from this 1, 2, and 2, 1 position is the x1, x2. I'm doing mentally a multiplication of this matrix times a row vector on the left times a column vector on the right. And I know that these numbers show up in the answer. The diagonal is the perfect squares. This off diagonal is a minus 2x1, x2, and there are no x1, x3s, and there are minus 2 x2, x3s. And I believe that that expression is always positive. I believe that that curve, that graph of this function, this is my function f, and I'm in more dimensions now than I can draw, but the graph of that function goes upwards. It's a bowl, or maybe the right word is forgotten. What's a long word for a bowl? Maybe paraboloid. I think paraboloid comes in. I'll edit the tape and get that word in. Bowl. let's say, is and if I could complete the squares. I could write that as a sum of 3 squares. And those 3 squares would get multiplied by the 3 pivots. And the pivots are all positive. So I would have positive pivots times squares. The net result would be a positive function and a bowl that goes upwards. And then finally, if I slice through this bowl, now I'm asking you to stretch your visualization here. Because I'm in 4 dimensions. I've got x1, x2, x3 in the base, and this function is z, or f, or something. And its graph is going up. But I'm in 4 dimensions, because I've got 3 in the base and then the upward direction. But now if I cut through this 4-dimensional picture at level 1, so suppose I cut through this thing at height 1. So I take all the points that are at height 1. That gives me, it gave me an ellipse over there in that 2 by 2 case. In this case, this will be the equation of an ellipsoid, a football, in other words. Well, not quite a football, a lopsided football. What will be, can I try to describe to you what the ellipsoid will look like? This ellipsoid. I'm sorry that I've ended the matrix right at the point. Let me be sure you see the equation. 2x1 squared, 2x2 squared, 2x3 squared, minus 2 of the cross products equal 1. That is the equation of a football. So what do I mean by a football or an ellipsoid? I mean that, well, I'll draw it here. It's like that, and like that. It's got a center, and it's got 3 principal directions, this ellipsoid. So you see what I'm saying? If we had a sphere, then all directions would be the same. If we had a true football, or it's closer to a rugby ball, really, because it's more curved than a football, it would have 1 long direction, and the other 2 would be equal. That would be like having a matrix that had 1 eigenvalue repeated, and then 1 other different. So the sphere comes from like the identity matrix, all eigenvalues the same. A rugby ball comes from a case where 2 of the 3 eigenvalues are the same. But we now have a case where, the typical case, where the 3 eigenvalues are all different. So this will have, how do I say it? If I look at this ellipsoid correctly, it'll have a major axis, it'll have a middle axis, and it'll have a minor axis. And those 3 axes will be in the direction of the eigenvectors. And the lengths of those axes will be determined by the eigenvalues. I can turn this all into linear algebra because we have the right thing we know about eigenvectors and eigenvalues for that matrix is what? Let me just tell you repeat the main linear algebra point. How could we turn what I said into algebra? We would write this A as Q, the eigenvector matrix, times lambda, the eigenvalue matrix, times Q transpose. The principal axis theorem, we'll call it now. The eigenvectors tell us the directions of the principal axes. The eigenvalues tell us the lengths of those axes. Actually, the half lengths are 1 over the eigenvalues, it turns out. And that is the matrix factorization, which is the most important matrix factorization in our eigenvalue material so far. That's diagonalization for a symmetric matrix, so instead of the inverse, I can write the transpose. Okay, so what I've tried today is to tell you what's going on with positive definite matrices. You see how all these pieces are there, and linear algebra connects them. Okay. See you on Friday.